A buffer is a solution that resists pH changes even when acid or base is added to it. We use two of these to calibrate our pH meters during the Ka of ethanoic acid lab. They are made by mixing a weak acid with a salt containing its conjugate base, or a weak base with a salt containing its conjugate acid. This means that you have a system with initial concentrations on both sides of the arrow. The following graph shows the pH changes of a buffer when adding acid and base. The buffer will start off at an initial pH level. By adding an acid, it will slowly and gradually change its pH, and then all of a sudden it will hit a point where pH change will occur rapidly. The same thing occurs if you take an initial sample of that buffer and add base to it. The region where the buffer resists pH changes is known as the buffer capacity. The size of the buffer capacity depends on the concentration of the buffer. The more concentrated buffer resists more pH changes, and the ratio of the conjugate pair components. If the weak acid and conjugate base are in a 1-to-1 ratio, then buffer capacity is at maximum. We can use the equations below as an example to explain why a buffer is able to resist pH changes. Here we have an ethanoic acid buffer system, where we add in 1 mole per liter of a weak acid and 1 mole per liter of its conjugate base. We can use Le Chatelier's principle to describe why this buffer will resist pH changes. If we add acid to the system, essentially what we are doing is we are increasing the hydronium concentration in the system. Because of this, it will cause a Le Chatelier shift to the left, using the common ion effect. By adding hydronium ion, it will speed up the reverse reaction because there are more reactants available. This means that the extra hydronium we added by adding the acid to the system will be consumed, and the pH will remain relatively stable. By adding a base to our buffer system, we are essentially adding OH1 minuses. These react with hydronium ions, making the concentration of H3O1 plus go down. Due to common ion effect, this will create a Le Chatelier shift to the right. The reverse reaction will go slower because it has less reactants, until the forward reaction has replaced the H3O concentration that was removed by the base. Now, a buffer can only absorb so much base or acid. Let's take adding base as an example as to why there is a limit. If you continue to add OH1 minuses, that will continually remove the H3O+, slowing down the reverse reaction. The forward reaction can go to replace the hydronium lost until one of the components run out. As long as you have ethanoic acid in your beaker, it can react with the water to replace the hydronium. As soon as this concentration goes down to 0, you can no longer use the forward reaction, and therefore you can no longer resist pH changes. Equilibrium calculations involving buffers are a little bit more complicated because you have to write the appropriate acid or base equation. You always write the equilibrium involving the weak acid or base, not the conjugate. The conjugate will appear on the product side. Stoichiometry must first be used to determine the initial concentrations of each chemical in equilibrium. There will always be a spectator ion which does not show up in your equilibrium equation. This is the other piece of the salt. You can't add a conjugate that is charged by itself. It always has to travel with the oppositely charged ion. Here's an example. A buffer is made by mixing 50 ml of 0.5 mole per liter acetic acid and sodium acetate solutions. The acetic acid is the weak acid, and the acetate in the sodium acetate salts is the conjugate. The Ka for acetic acid is 1.8 times 10 to the minus 5, and we want to calculate the pH of the buffer. We'll start by writing the equilibrium equation for acetic acid reacting with water. If I find the hydronium concentration at equilibrium, that will give me the pH of my buffer. Because we are adding two solutions together, we can find the initial concentrations of both the acetic acid and the acetate by pretending that this is a dilution and using the equation from grade 11, C1V1 equals C2V2. Where V2 would be 100 ml because we're adding 50 ml of each solution. That essentially means that we are going to be cutting our concentrations in half. Because this is an acid equilibrium, I need to solve my concentration using a Ka. Now don't be tempted to cross these two brackets out. They are not exactly the same. But I do want to try to avoid quadratic formula. If I do my assumption and take my lowest initial concentration, 0.25, and divide it by the constant, that equals greater than 500. That means that if I take 0.25 and subtract x from it, I'll get 0.25. That also means that if I add x to 0.25, I will also not get a change. That makes the math very simple. The pH in my buffer will be the negative log of x, which equals 4.7.